Okay, welcome to lecture 26. We're still in unit 3 working on the Laplace transform. And today we're going to look at the Laplace transform of a couple of special functions, one called the unit step function and one called the Dirac delta function. And this is going to lead us to something called the second translation theorem. Okay, and this is basically going to allow us to take or to solve ODEs with some challenging non-homogeneous terms. Okay, so you'll see what I mean soon. So the first thing I'll do is introduce to you something called the unit step function. So the unit step function is sometimes called the Heaviside function. That's not a misspelling, that's named after someone with the last name Heaviside. Okay, but this unit step function is a piecewise continuous function, which is 0 when t is between 0 and a, and 1 when t is greater than or equal to a. Okay, and we write this unit step function as this very stylized u, t minus a. Okay, so of course a could be 0, of course, so we could just have the stylized u of t, which would mean that, well, the function is just equal to 1 for t greater than 0. But basically, what does this function look like? Well, for t a equal to a or less, this function is equal to 0, and then at the point t equals a, the function jumps up to be equal to 1 there. Okay. So this unit step function, or this Heaviside function, can be used to clip a function. So what do I mean by that? Well, let's just consider the linear equation f of t equals t minus 1. So again, we've just got a linear function here. It passes through the y-axis, it cuts the y-axis at t equals 0, y equals negative 1, or f of t equals negative 1. If instead of plotting f of t equals t minus 1, I plot t minus 1 multiplied by the unit step function at t minus 2, so here a is equal to 2. So everything for every this combined function, or this multiplied function, for every t less than 2, this new function is going to be equal to 0. Okay, so between t equals 0 and t equals 2, our function is equal to 0, and then after t equals 2, we jump up back to the original function t minus 1. Okay, so we can clip a function. Instead of having this function being linear all the way, we have a linear part preceded by a part that is 0. Okay, we can also use the unit step function to combine two distinct functions into a single piecewise function. So for example, if I want the function f of t to be equal to some function g of t when t is 0, between 0 and our number a, and then equal to h of t, so some separate function when t is greater than or equal to a, then I can write this as g minus g times u of t minus a plus h times u of t minus a. Okay, how does this work? Well, this first part here, until t equals a, so for t less than a, this term here is 0, right? Because the Heaviside function, or the unit step function, is 0 there. So I just get g of t. Then when t is greater than or equal to a, then this Heaviside function is equal to 1. So I get g of t minus g of t, which is 0. And similarly, this part of the function is equal to 0 until t equals a, and then the unit Heaviside function, unit step function, becomes 1. And so for t equals a or greater, this function is just equal to h of t. And so if I plot that, I have for t less than a, I have the function g of t. And then as soon as we hit t equals a, I jump down onto the second function h of t. Okay. So these type of approaches can be useful for things like signal processing. So you can get some differential equation in signal processing and engineering, and these type of functions can come up in those situations. Okay, so now that we've learned something about how the unit step function works, what we might like to know, well, what happens if we take the Laplace transform of the unit step function, or let's say the Laplace transform of something multiplied by this unit step function. Okay, so we get something that we're going to call t-translation. So the unit step function can be used to translate a function along the horizontal axis. Well, let f of t be some function defined for t greater than 0. If I take f of t and I instead combine it with this unit step function, so f of t minus a times this unit step function at t minus a. So notice that the t minus a must be the same here. T minus a, f of t minus a, so that shifts f a units to the right, and t minus a in the unit step function here. Well, this product is equal to 0 for t less than a, because the second part here, this unit step function, is equal to 0 for t less than a, and it's equal to f of t minus a for t greater than or equal to a, because there the unit step function, or the Heaviside function, is equal to 1 there. And it has the effect of shifting the function f of t along the horizontal axis by a units. Okay. So we shift this function f of t across a units, and then we just set the function equal to 0 for t less than a. Okay, so this leads us to the second translation theorem, which is a t-translation of a function by the unit step function. Okay, so the first Laplace translation theorem, which we learned earlier in this unit, is if we have a function f of t and we multiply it by the exponential of a times t, if we take the Laplace transform of that product, then we get the f of s minus a. We get an s translation in this case, and for the first translation theorem. Okay, so that first translation led to a translation in the s domain, right? And we should be quite familiar with this now, because we've done quite a few examples in class. The second translation theorem is as following. So f of s, we recall, is the Laplace transform of f of t, and if a is greater than 0, then the Laplace transform of f evaluated at t minus a multiplied by the unit step function at t minus a is equal to e to the minus a times s times f of s. Okay, so this is a translation in the t domain. The first translation theorem was a translation in the s domain. The second translation theorem is a translation in the t domain. And you'll notice it results in exponentials in both cases, right? So the first translation theorem had an exponential in the t domain. The second translation theorem has an exponential in the s domain. Okay, well, the proof of this is not too hard. I'll show you how to practically use this shortly. But first, let's look at the proof of this. Well, I can solve this Laplace transform by definition. So, well, you can either use the limit as n goes to infinity case, or in this case, I'm just going to use the improper integral way of writing this. So we get the integral from 0 to infinity of e to the minus st times the function that we're trying to evaluate the Laplace transform of. Okay, well, I can split this integral up because if you recall, we're allowed to split up integrals. And I'm going to split this up into two parts. The first one being the integral from 0 to a, and the second one being the integral from a to infinity, so that these two lines are equivalent. But if you recall, for t less than a, this unit step function is equal to 0. So this integral is equal to 0. So we quite simply get that this first part of this integral disappears as 0. Similarly, in the second integral here, for t greater than a, or greater than or equal to a, this unit step function is equal to 1. Okay, so I just get, in fact, I can just replace this with 1. So I get the integral from a to infinity of e to the minus st times the function evaluated at t minus a dt. Okay. Now I'm just going to do a substitution. So I'm going to create a new variable v, which I'm going to say is equal to t minus a. Okay, if I take the derivative, dv equals dt, so things are quite simple there. But it's worth noting that when t equals a, v is equal to 0. Okay, so therefore I can write my this integral in terms of v now, instead of t. So I get this Laplace transform is equal to the integral from 0 to infinity now, because remember when t equals a, v equals 0, so we get the integral from 0 to infinity of e to the minus s times v plus a, because here t is equal to v plus a, so I'm replacing this t in here by v plus a, times f of v, because v is equal to t minus a, so this t minus a is equal to v, and dt equals dv. Okay, so I've performed the substitution now. What I can do is I can split this exponential up into two parts using the exponential law, so the product of two exponentials. So this is equal to e to the minus a times s times the integral from 0 to infinity of minus s times v, f of v dv. Okay, but what is this integral? Is quite simply the definition of the Laplace transform of f of t. So in fact, the Laplace transform of f evaluated at t minus a multiplied by the unit step function at t minus a is just equal to e to the minus a times s times the Laplace transform of f of t. Okay, you could call it the Laplace transform of f of v, but essentially it's the same thing. So this is equal to e to the minus as times f of s, and that completes the proof. So it's a fairly straightforward proof. Okay, so let's look at an example. So now we want to take the Laplace transform of t times the unit step function at t minus 2. So this is not quite in the right form, right? Now this is not quite in the form f of t minus a times unit step function of t minus a. Of course here a is 2. So what I'm going to do is I'm going to write t as t minus 2 plus 2, right? Because if I take t, if I subtract 2 from it and I add 2 to it, then I get the same thing back, right? Okay, then if I do that, what do I get? Well, I get a t minus 2 multiplied by the unit step function, or the unit step function at t minus 2. So this t minus 2 bit here now is in the form of the second translation theorem. I also get this extra bit 2 times the unit step function at t minus 2. Okay, so just writing that out. So now this first Laplace term here is exactly in the form of the second translation theorem. So here a is equal to 2, and well, the Laplace transform of t, let's recall what that is. The Laplace transform of t is just 1 over s squared, right? So this first term here is going to be 1 over s squared times e to the minus 2 times s. Okay, and that's evaluated here. Notice that the second term though is also, even though it doesn't look like it, it is actually also in the same form for the second translation theorem, because 2 is a constant. So if I evaluate 2 at t minus a, it's still equal to 2 because it's a constant. And the Laplace transform of 2 is just 2 over s. So I quite simply get 2 divided by s times e to the minus as, or e to the minus 2s. Okay, and I can pull out the common factor of e to the minus 2s. So maybe an important thing to note is that the Laplace transform of the unit step function itself, so 1 times the unit step function, is always equal to e to the minus as over s. And again, that's because if our function multiplying the step function is just 1, f of t is 1, f of t minus a is 1, in fact f of t minus anything is 1, because 1 is just a constant, regardless of the value of the variable t. So this is worth remembering because it will come up time and again in assignments and such. So let's look at an example going the other way now. So this is often the way we'll see these problems. We're looking at the inverse Laplace transform of some exponential times s over s squared plus 2 squared. Okay, so a here, a in terms of the second translation theorem, is equal to minus pi over 2. Okay, minus pi over 2 in this exponential here. If I didn't have this exponential term in here, I'd be finding the inverse Laplace transform of s over s squared plus 2 squared. And if you recall, that was a cosine. Okay, so if I just ignore that exponential term here for a moment, and I took the inverse Laplace transform of what's left, I know that that would be equal to cosine of 2t. Okay, therefore, the inverse Laplace transform of that thing times the exponential, well, what is it going to be? Well, I'm going to be multiplying, my a here is minus pi over 2, my f of s is s over s squared plus 2 squared, therefore my f of t is cosine of 2t, then I have to evaluate that cosine of 2t at t minus a. So this is going to be the unit step function at t minus, or let's say t plus pi over 2, times cosine of 2t, where t is replaced by t minus a, so t plus pi over 2. Okay, so this should actually be a plus here. So I get cosine of 2t plus 2 times pi over 2 times the unit step function at this point here. In fact, actually, a should be positive pi over 2. In the second translation theorem, it's exponential of minus as. So in fact, this a should be positive pi over 2. So this is written correctly down the bottom here. A equals negative pi over 2 is the thing that's written incorrectly. It should be positive pi over 2. Okay, well I can simplify this if I want, because 2 times pi divided by 2 is just pi. So 2 times t minus pi. If I take cosine and I subtract pi from it, I always get negative cosine. So I get negative cosine of 2t times the unit step function at t minus pi over 2. Okay, another example. So we're trying to find the inverse Laplace transform of e to the minus s times two fractions. Okay, so again, this is in the correct form for the second translation theorem, because I have some function of s multiplied by this exponential term. Okay, so I'm just going to, the inverse Laplace transform is linear, so let's do this term by term. Okay, so f of s in this first term here is 1 over s, okay? So if I completely ignore this exponential and I took the inverse Laplace transform of 1 over s, I'd quite simply, what would I get? Well, I would just get 1, right? Laplace transform of 1 is equal to 1 over s. So when I take the inverse Laplace transform of 1 over s times this exponential, here a is equal to 1, f of t is equal to 1, because the inverse Laplace transform of 1 over s is equal to 1. F of t minus a is still going to be equal to 1 because, well, a constant is a constant no matter what value of t you use. So this first term here is going to, the inverse Laplace transform is going to be 1 times u of t minus 1. Okay, so this is quite a simple one, u of t minus 1 here. The slightly more challenging one is this second term here. Okay. Again, if I ignore the exponential here, 1 over s plus 1, the inverse Laplace transform of that is the exponential of minus t. Okay, so f of t is exponential of minus t. F of t minus a, here a is 1, so f of t minus 1, we're going to have exponential of negative t minus 1 multiplied by this unit step function. So here I get this first term here is just the unit step function of t minus 1 minus the second term here, unit step function at t minus 1 times e to the negative t minus 1. If I did not have this exponential term here, then this term would just be e to the minus t without the unit step function. The exponential in the s here, this is what shifts our t back 1 unit. Okay, so that's why we have a t minus 1 here. Okay, so it's worth going through the study guide and the textbook for a few more practice of these ones, because these can be quite challenging to visualize in your mind. But again, it really relies on knowing your inverse Laplace transform, knowing the table. So now we're going to look at our second type of function here, special function, and it's called the Dirac delta function. So before we get to the specific Dirac delta function case, we're going to look at something very similar called the unit impulse. So a unit impulse function is a function where the value is equal to 0 initially. It switches to the value 1 divided by 2a at some value of t, and then switches back to 0 again. Okay, and it's represented by this piecewise equation here. So we use a delta, a lowercase delta Greek letter, to tell us that we're using a unit impulse function. The a that we were talking about here is down below as a subscript here. Value at t minus t naught. So t naught is that position where the function is switching. Okay, a has to be greater than 0 and t naught has to be greater than 0. And so, well, let's just plot this thing actually. So at t naught minus this number a, the function switches from being 0 to being the value of the function being 1 over 2a. Okay, and it stays at that value of 1 over 2a until the point t naught plus a, where it switches back to 0. Okay, and one important property is that the area under this curve here, so this sort of square block in the middle, or rectangular block in the middle, that area is equal to 1. So if I integrate this function, this unit impulse function, from 0 to infinity, this is equal to 1 no matter what value of a is here. And if you think about it, if a becomes smaller, then the width of this unit impulse becomes smaller, but the height becomes larger because we're dividing through by a smaller number, 1 over a, or 1 over 2a. So this function is designed in a very specific way. As you close this gap here, this impulse becomes larger, in the way that it always has the area of 1 underneath this curve, no matter what the value of a is. Okay. Okay, well, of course you can evaluate this function because it is 0 outside of the limits t naught minus a, t naught plus a, and it's 1 over 2a inside those limits. So you can easily evaluate that and prove to yourself that that is equal to 1. Okay, but what happens in the limit as a goes to 0? So as a goes to 0, this gap here becomes smaller and smaller and smaller, and the function becomes larger and larger and larger. So in the limit as a goes to 0, we just drop this subscript a here and just write this delta function here. So this delta at t minus t naught is equal to the limit as a goes to 0 of delta a. Okay, and we call this the Dirac delta function. So this delta function here is called the Dirac delta function. The limit still satisfies the integral from 0 to infinity of this Dirac delta function is still equal to 1, even though it has finite width. Basically, it has infinite height as well, in fact, this Dirac delta function. And that's because this Dirac delta function at t equals t0 is equal to infinity, or approaches infinity, and it's 0 outside of that t0. So it's not a usual function, but we call it a generalized function. Okay, and we can actually take the Laplace transform of this Dirac delta function. So the Laplace transform of the Dirac delta function at t minus t0 is equal to the exponential of minus s times t0. So you can sort of see that this is going to be related to that second translation theorem, because we're going to get an exponential in the s domain here. So recall that the limit of some function that we've taken the Laplace transform of, the limit as s goes to infinity of this function must be equal to 0 for any transform function f of t. But the Laplace transform of delta t, that limit is going to be equal to 1 as s goes to infinity. Okay, so this is not a usual type of function here. This is not going to be a usual type of function. Okay. But how is it actually used? Well, let's solve an ODE involving special functions. Okay. So, well, here are some relations that we've learnt in this lecture so far. We've learnt that the Laplace transform of the Dirac delta function is e to the minus s times t naught. We have the second translation theorem in this next line here, and we have the first translation theorem in the third line here. Okay, so we've got the initial value problem with two very simple initial conditions. I've got the second derivative of y plus 2 times the first derivative of y plus y itself equals, now our non-homogeneous term is a Dirac delta function. Okay, with t0 equal to 1. We're going to take the Laplace transform of both sides of the ODE. So again, y double prime here is, we know that if we take the Laplace transform of y double prime, we get this expression here. But both our initial conditions are 0. So these two terms here are going to be 0. Plus 2 times the first derivative of y. Again, this is the first derivative, the Laplace transform of the first derivative of y. And again, this initial condition is going to be 0. Plus y, so Laplace transform of y of t gives us capital Y of s. Then we just need to take the Laplace transform of our Dirac delta function, but we know that that is equal to e to the minus s naught, e to the minus s times t naught. T naught here is 1, so we just get the exponential of minus s. Simplifying that equation with the initial conditions that we have, and then solving for the common factor of y, we get s squared plus 2s plus 1, all multiplied by y of s is equal to this right hand side e of minus s. Okay, algebraically solving that for y and noticing that that denominator can be written as s plus 1 squared, I can now try and evaluate with the inverse Laplace transform of y of s to find the solution to the initial value problem y of t. Okay, so that is equal to the inverse Laplace transform of e to the minus s over s plus 1 squared. Okay, so let's for a minute ignore this exponential term. If I had 1 over s plus 1 squared, and I was trying to take the inverse Laplace transform of that, what would I have? Okay, well again, this is going to be a shift theorem or a first translation theorem case, because if I had 1 over s squared without the plus 1, I would just get t, right? But because I have the plus 1 as well, I can use the first translation theorem to multiply my t by exponential of negative t, because this is shifted by negative a, so negative 1. So if I didn't have this exponential of negative s, the inverse Laplace transform would be t times the exponential of negative t. Okay, but I do have this negative s, so I should use this first translation theorem as well. So whenever I see f of t, I have to replace the t with the t minus a. So in fact, I'm going to get instead of t times e to the negative t, I'm going to get t minus 1 times e to the negative t minus 1. And then, of course, multiplied by my unit step function. So here we go, t minus 1 times e to the negative t minus 1 times that unit step function here. Okay, great. And, well, there is another Laplace transform property that we've used, but again, I kind of expect you to remember these now, or at least to refer to them on the table of useful information. So, not only do we have the advantages that we talked about in the previous lecture for solving ODEs or initial value problems using the Laplace transform, but now we can solve Laplace transform problems that have these special functions in the Dirac delta function. And so these are quite useful for signal processing problems where you have switches that turn on and off at various times. So they do have some practical applications which we can't solve using any other method that we've learned so far in this class. So this Laplace transform method is really quite useful. Okay, so in the next class we'll look at maybe one more example and learn how to solve some of these problems in MATLAB or Octave. Okay, thank you.